Today I'm going to talk about our last big unit in BC Calculus, which is on power series. We talked about different ways to write power series. The most general form is using the Taylor definition for power series, the nth derivative, the exponent, and the factorial. But we also looked at two shortcut techniques using geometric series and also using binomial series. I'll also review in this unit how to analyze the radius, the interval of convergence, approximating the error with Taylor polynomial, both AST and Lagrange. And lastly, I'll talk about some different applications, like how you use power series to do integrals and summations. So first thing I'm going to do is take this function, f of x equals 2 over 3 plus 4x, and just look at it in a variety of different formats and settings. I'm going to start by writing the Taylor series for it. I'll look at some error questions, and so on and so forth. So this is going to be a really long example that I'm going to do here. First thing I want to do is just write the Taylor series for f of x centered at 0 and find its interval of convergence, but I'm going to do this two ways to demonstrate our two techniques. I'm going to start with our Taylor definition. Now it's centered at c equals 0, so technically this can also be called a Maclaurin series, or I can just call it a power series centered at 0 as well. But either way, I'm going to use the definition with the derivatives. So I'm going to find f of 0, which is equal to 2/3. And then I'm going to go through the derivatives until I find a pattern for this. So f prime of x is going to equal negative 2, 3 plus 4x to the negative 2 times 4. And therefore f prime of 0 is going to equal negative 2, 3 to the negative 2 times 4. Now I'm not going to multiply it together because I'm going to try to look for a pattern with these numbers. F double prime of x, I'm going to get 4, 3 plus 4x to the negative 3. There's a 4 from the original one, and now there's 4 squared for the second chain rule. So f double prime of 0 is equal to 4, 3 to the negative 3, 4 squared. I'm going to do another one just to look for the pattern. So f triple prime of x is going to equal negative 12. 3 plus 4x to the negative 4. This one's going to be 4 cubed. So f triple prime of 0 is going to equal negative 12, 3 to the negative 4, and 4 cubed. So if you notice, I've got powers of 4 here. I've got powers of 3 to a negative value. And I have these numbers in front, 2, 4, and negative 12. But notice if I factor out a 2, this becomes 2 times 1. This becomes 2 times 2. The next one is 2 times 6. And in fact, if I did another one, it would be 2 times 24. So we're looking at factorials with that first part there. Just all the factorials are being multiplied by 2. So the nth derivative of f, evaluated at 0, it's an alternating sign, notice, because it goes positive, negative, positive, negative. So we're looking at negative 1 to the n. There's that 2 that I showed you. There is a factorial, so n factorial. There's 3 to a negative power, and notice the negative power is 1 more than the derivative. So I'm going to write 1 over 3 to the n plus 1. And then 4 is being raised to the same power as the derivative, so 4 to the n. So our Taylor series definition for this would be summation n equals 0 to infinity. Our nth derivative, so negative 1 to the n, 2 n factorial, 1 over 3 to the n plus 1, 4 to the n, times an exponent, x minus 0 to the n, because it's centered at 0, all over n factorial. Now I'm going to simplify this a little bit. N factorials cancel out, so we can also write this as n equals 0 to infinity, negative 1 to the n, 2 times 4 to the n, x to the n, and, all over 3 to the n plus 1. Now, that's obviously the very long way to do it because I also showed you another way to set this up using geometric series. But I wanted to show you that both ways give you the same answer. So, going back to my original problem, it was f of x equals 2 over 3 plus 4x. And I want this to be centered at 0. So basically I'm going for that a over 1 minus r setup. So I'm going to factor out a 3 from the denominator. Rewrite this as 2/3, 1 plus 4x over 3. And there's my a over 1 minus r kind of a setup. So the summation for this would be n equals 0 to infinity. A is 2/3. R is negative 4x over 3 to the n power. Now, we should see the same thing either way. So notice I've got the -1 to the n. I've got 2/3 right here. There's my 2/3. And then 4 to the n, x to the n, and 3 to the n are all in there. So you get the same thing whether you use a over 1 minus r or if you use the Taylor series. The interval of convergence for this, because it is a geometric series, all we need to do is look at this ratio, absolute value of -4x over 3, and set it less than 1. We don't need to worry about when it equals 1, the endpoints, because it is a geometric series. So we already know it's going to diverge when the ratio is equal to 1. So solving this, you're going to get -3/4 is less than x is less than 3/4. So that's my interval of convergence for this. Alright, so two ways to do the same series, one using the Taylor definition, and then the other one just using our a over 1 minus r technique. Part B, what I want to do is approximate the error if a fourth degree Maclaurin series is used to represent f of 0.6. So I'm going to go up to my definition up here, and basically look at what this would be. So, my series was n equals 0 to infinity, 2/3 -4x over 3 to the n. This is what f of x equals. Now, I'm going to use a fourth degree Maclaurin, and I guess this should be technically polynomial. And so if I were to write out the fourth degree Maclaurin polynomial, then it's not f of x equals anymore, it's f of x is approximate, because I'm only using a partial sum of the entire series. So writing out to the fourth degree, I'm going to have for my first term 2/3, because when n equals 0, the rest of it is equal to 1, plus 2/3 times -4x over 3, plus 2x times -4x over 3 squared, plus 2/3 -4x over 3 cubed, plus 2/3 -4x over 3 to the fourth. So that is an approximation of f of x because I'm only using so many terms. Now do notice though that it is an alternating series though. The first term is positive, then negative, the third term is square, so technically it's positive, and so on and so forth. So for this to approximate the error, I can actually use the alternating series test and use the first omitted term. What this means is that f of 0.6 is approximately equal to 2/3 plus 2/3 times -4 times 0.6 over 3, so on and so forth, out to 2/3 -4 times 0.6 all over 3 to the fourth. And therefore my error is bounded by my first omitted term. So the first omitted term in here is going to be 2/3 -4 times 0.6 all over 3 to the fifth power. There's my part B error. And don't worry, I'll do more errors as we go along. Okay, part C says write a Taylor series for f of x centered at c equals 1. Now, even though it says Taylor series, that doesn't mean you're forced to use the definition with the derivatives, because again, a Taylor series is just a power series, and we've learned now several different ways to take a power series. So for this one, f of x equals 2 over 3 plus 4x. I'm going to use my a over 1 minus r method instead. So centered at 1, what that means is I want to ultimately write a power series n equals 0 to infinity, a sub n, x minus 1 to the n. So I'm going to go ahead and put that x minus 1 in now, so I don't have to like algebraically get it there later. Now technically what I've added is a -4 to the denominator, so I need to add a 4 to make sure that I don't change my original problem. Rewriting this, that means I have 2 over 7 plus 4, x minus 1, 2/7 over 1 plus 4, x minus 1 over 7. So, writing this in, from our a over 1 minus r formula, the power series is n equals 0 to infinity, 2/7 for my a, -4, x minus 1 over 7, all raised to the n for my r part of the series. The last two ones I'm going to look at are basically taking functions and manipulating them into an a over 1 minus r so that I can work with it. So notice in the part D, I have g of x equals negative 8 over 3 plus 4x quantity squared. The squared in the denominator should give you an indication that we're possibly looking at a derivative of an a over 1 minus r, because when you take something to the negative 1 power and take its derivative, you get something to the negative 2. So here's one way you can kind of think of it. If you were to integrate negative 8 over 3 plus 4x quantity squared, let's see, so technically that would come from a negative 1 power. So we know we have 3 plus 4x to the negative 1. If I take the derivative of that, I'll get a negative in front. 3 plus 4x to the negative 2. I have a 4 from chain rule when I take the derivative. Now that's an 8 in front, 8 up here. So what that means is I need a 2. So that would be negative 2. 3 plus 4x to the negative 2 power times 4, and I believe that would equal what we had before. So notice, and I did that on purpose, is that that's the same power series I worked with just a bit earlier. So if the integral of negative 8 over 3 plus 4x squared is equal to 2 over 3 plus 4x, then to work it the other way, negative 8 over 3 plus 4x quantity squared must be the derivative of 2 over 3 plus 4x. And I found the Maclaurin series for 2 over 3 plus 4x. That was series n equals 0 to infinity, 2/3, negative 4x over 3 to the nth power. So now I want to take the derivative with respect to x. So that's going to be the series 2/3 n for my power rule, negative 4x over 3 to the n minus 1. I need a negative 4/3 when I take the derivative for chain rule. And then the last thing I need to check is my index. So since it's n minus 1, I can't start from 0 anymore because that would give me a negative power. So now it's from n equals 1 to infinity instead. So I'm going to double check, and yes. Okay, now let's look at it the other way. H of x equals 1/2 natural log of 3 plus 4x. So this time, instead of taking the integral, I'm going to look at the derivative, because you should remember that the derivative of ln is 1 over something. So the derivative of 1/2 ln of 3 plus 4x would equal 1 over 2 quantity 3 plus 4x times 4 because of chain rule, and lo and behold, that simplifies to 2 over 3 plus 4x, which is the example that I've been working on. So if I take the derivative of 1/2 of ln 3 plus 4x, and I get 2 over 3 plus 4x, then basically what I have to do is say that 1/2 natural log of 3 plus 4x has to equal then the integral of 2 over 3 plus 4x. Now, here's the problem though. If I were to integrate that as is, I would end up with natural log, but I'd also have a plus c. So to get rid of the plus c, what I usually do, and I know this is different from the book, is I rewrite this as a definite integral. So I'll write 2 over 3 plus 4t dt. That still gives me my natural log. I have to figure out the bounds that I'm going to substitute into this so that I get 1/2 ln of 3 plus 4x. I'm going to put an x in top because then I get my ln of 3 plus 4x. But I need to put a value in the denominator so that when I subtract my second half, I get 0. Now, ln of 0 ln of 1 equals 0. So the value of x that's going to make this 1 is going to be negative 1/2. So that has to be my lower bound as a result. Okay, I've already beat this series to death, but I'm going to do it just one more time here. So, integral from negative 1/2 to x. This time I want to use the Taylor series that I found in part C to put this together. So the Taylor series I had in part C, I believe, was n equals 0 to infinity, 2/7, negative 4/7, in this case t minus 1, all raised to the n. And I'm going to integrate this with respect to t. I usually try to simplify the integrand before I start integrating. That way I don't make a mistake or have to worry about too much u substitution as I put it together. So I'm going to rewrite this as from negative 1/2 to x, the series n equals 0 to infinity. 2/7 I'll leave there. negative 4/7 to the n, I'm going to separate out, and I'll make it t minus 1 to the n dt. This way, when I integrate it, I don't have to worry about too much u substitution to correct for as a result. So integrating with respect to t, anything with n's are constants. So this will be n equals 0 to infinity. 2/7, negative 4/7 to the n is my constant. So t minus 1 to the n plus 1 all over n plus 1 would be undoing the power rule. And my bounds are from negative 1/2 to x. Substituting in, that means my power series for this function would be n equals 0 to infinity, 2/7, negative 4/7 to the n, x minus 1 to the n plus 1 all over n plus 1 minus, and notice I am actually going to have a second half to this because of the way that I had to set on my integral. So n equals 0 to infinity, 2/7, negative 4/7 to the n, and this part will be negative 1/2 minus 1 to the n plus 1 all over n plus 1. Normally that second half goes away, but because of the function that I was working with, ln of 3 plus 4x does get a little bit more complicated. What the book does is it sets up the indefinite integral, has a plus c, and then uses an initial condition to solve for the c part. So what you would say here is that when x is negative 1/2, ln is equal to 0, and you would get the same thing for your plus c terms. Okay, that is enough of that one. I'm going to do something similar, but not quite overkill with x squared sine x, just to kind of emphasize the different ones, different summations that I want to recommend that you memorize. So, let's start with writing the Maclaurin series for this. F of x equals x squared. Sine x is one of those series that I told you to memorize. N equals 0 to infinity, negative 1 to the n, 3x to the 2n plus 1, all over 2n plus 1 factorial. But again, that's not quite in power series form. Power series, I need it to look like a sub n, x to the n, or some variation on that. So I'm going to take that x squared and move it in. However, I don't want to write x to the 2n plus 3 because the 3 isn't being raised an extra 2 powers. So what I have to do is same thing as before, separate this out. It's still going to be negative 1 to the n. I want to leave 3 to the 2n plus 1, but this time x is going to be to the 2n plus 1 plus an extra 2 all over 2n plus 1 factorial. So the summation for this, negative 1 to the n, 3 to the 2n plus 1, x to the 2n plus 3 all over 2n plus 1 factorial. And that was the first part. Okay, second part. I'm going to take the same function, x squared sine x, I believe. And this time I want to write a second degree Taylor polynomial to represent the function centered at c equals pi over 6. So I'm going to write this before I forget. Now, this time I can't use my Maclaurin series definition because it's centered at pi over 6, and the Maclaurin series is centered at 0. So I'm going to have to just brute force, work through the different derivatives, and then write the expression out. Let's start with pi over 6. So f of pi over 6 is going to equal pi squared over 36. Sine of 3 pi over 6 is sine of pi over 2, so that's equal to 1. First derivative, f prime of x. I'm going to have to do some product rule here. So first times the derivative of the second, 3 cosine 3x, plus the second function times the derivative of the first. So f prime of pi over 6. First part is going to be pi squared over 36 times 3. However, cosine of 3 pi over 6, or cosine of pi over 2 is 0, so I actually don't have to worry about that part. The second term here is going to be 2 times pi over 6, so pi over 3. Sine of 3 pi over 6 is again pi over 2, so sine of pi over 2 is 1. So all I'm left with here is pi over 3 as a result, I believe. First part is 0, second part pi over 3 times 1, yes, okay. Second derivative, f double prime of x. You're going to get product rule again. So 3x squared times negative sine 3x plus cosine 3x times 6x. And another product rule. Sine 3x times 2 plus 2x times 3 cosine 3x. Substituting in pi over 6, f double prime of pi over 6. Let's see, the first term has a sign, so that part's going to be there. So that'll be 3 times pi squared over 36 times another negative 3 times 1. Second term is going to be 0 because cosine of 3 pi over 6 is 0. Third term, we're going to get 2 times sine of pi over 2, so that's 1. And then the last term is 0 also. So this is going to simplify to negative 9 pi squared over 36 plus 2, or 2 minus pi squared over 4. How about? Alright, so now each term is going to have a derivative piece of information, an exponent, and a factorial. So just kind of writing out the Taylor pieces, the first one's going to be f of pi over 6, centered at pi over 6, so x minus pi over 6 to the 0 over 0 factorial. The next one, f prime of pi over 6, x minus pi over 6 to the first over 1 factorial. And then the third term, f double prime of pi over 6, x minus pi over 6 squared over 2 factorial. And I did ask for a second degree Taylor polynomial, thankfully, so I don't have to look at any other terms. So substituting in my values, the first one's going to be pi squared over 36, x minus pi over 6 to the 0 over 0 factorial, plus my prime was pi over 3, x minus pi over 6 to the first over 1 factorial. And then the next one was 2 minus pi squared over 4, x minus pi over 6 squared over 2 factorial. And there's my second degree Taylor polynomial of the function centered at pi over 6. The last thing I'm going to do is Lagrange with this to estimate the error using a first degree Taylor polynomial to represent f of pi over 2. So I did this on purpose so that I wouldn't have to take another derivative. Basically what I want to do is just use the first two terms from this and say, well, what if I just use that to represent f of x? And the question is, what would be my error from that? So Lagrange error basically is the first omitted term. So in this case, since I'm using up to the first degree, my error is going to be bounded by the first omitted term, which is the second derivative. So I need to find the maximum value of my second derivative, x minus c to the second, all over 2 factorial. Now, just to kind of review, this was centered at pi over 6. So my center is pi over 6. My value of x, where I'm trying to evaluate it, is x equals pi over 2. And therefore, I need to try to find the maximum value of f double prime of x between pi over 6 and pi over 2. So what I did was I graphed the f double prime of x that I had from before. Just to remember, f double prime of x was equal to, I simplified it out, negative 9x squared sine of 3x plus 12x cosine 3x plus 2 sine 3x. I want to make sure that's what it simplifies to. Negative 9x squared sine x plus 12x cosine 3x, because these two add up to 12x, and then 2 sine 3x. And like I said, it's complicated enough that basically what I did was I graphed that function, found the maximum value. The maximum value was at x equals pi over 2. And if I substitute in pi over 2, I believe I came up with 9 pi squared over 4 minus 2 as the largest value. So let's see if that makes sense. At x equals pi over 2, if I substitute it in, I get negative 9 pi squared over 4. Sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. And then the last part is minus 2. So that checks out. So that's my maximum value. So the error then is less than or equal to 9 pi squared over 4 minus 2 for the maximum value of my second derivative in that interval. My x was pi over 2 minus my c, which is pi over 6, that squared all over 2 factorial. So that would be the bounds of my error using Lagrange. And I think that example is now done. I wanted to look at other types of problems we did. Obviously, we did more than just writing, so I wanted to review how to find interval of convergence, some of the theorems we came up with that expression as well. So here, to find the interval of convergence, first you have to figure out the range that you're looking at. So we're going to take the limit as n approaches infinity of negative 1 to the n plus 1, x plus 3 to the n plus 1, n plus 1, 5 to the n plus 1, divided by the nth term, negative 1 to the n, x plus 3 to the n, and 5 to the n. And basically what I'm doing is I'm applying the ratio test from our last unit, finding the values of x and make the ratio less than 1. Because of this n here, we're not looking at a geometric series, and the only reason the n is going to cancel out is because we'll ultimately take the limit as n approaches infinity. So as n approaches infinity, n over n plus 1 approaches 1, which is why that cancels out. And then the rest of it, when I simplify it, becomes the absolute value of x plus 3 over 5. So solving this out, I get negative 5 is less than x plus 3 is less than 5. And then keep on going, I get negative 8 is less than x is less than 2. Alright, so stop at this point. I want to review radius of convergence. My center is at negative 3 because it's x plus 3, and therefore these units here are 5 units away from the center, so the radius of convergence is 5. Now, that's just to find the radius of convergence. To find the interval of convergence, what I have to do is check the endpoints and see if they converge at either end of those values. So let's start with x equals negative 8. If I substitute x equals negative 8 into my original function, I get negative 1 to the n, negative 5 to the n over n, 5 to the n. That simplifies to 1 over n, which diverges by p series. If I substitute in my other endpoint, x equals 2, into my function, I get the series n equals 0 to infinity, negative 1 to the n, 5 to the n over n, 5 to the n. So that simplifies to negative 1 to the n over n. Negative 1 to the n means I'm going to use AST. So you take the limit as n approaches n approaches infinity of 1 over n. You get 0. You check that it's decreasing. It is. And therefore it converges by AST. So my interval of convergence, meaning what are all the values of x that can make this series converge, is from negative 8 to 2. But at negative 8 it diverges, and only at 2 does it actually converge. So that would be the interval of convergence for f of x. Now, for f prime and the integral of f, I don't have to do my ratio test anymore because I know it's going to be the same range of values, but I do need to double check the endpoints because the endpoints could be different. So just to rewrite it for myself here, f of x was originally n equals 0 to infinity, negative 1 to the n, x plus 3 to the n, all over 5 to the n times an n. So let's start with f prime. Okay, so f prime, I'm going to take the derivative with respect to x. So negative 1 to the n is a constant. I'm going to have n x plus 3 to the n minus 1, all over n and 5 to the n. I have to make sure my index is okay, so this time I have to change it from 1 to infinity. Nicely enough, the n's cancel out. So I'm only going to look at the endpoints for this, which is at negative 8 and at positive 2. So at x equals negative 8, my series becomes negative 1 to the n, becomes negative 5 to the n minus 1, all over 5 to the n. This is going to simplify to n equals 1 to infinity. This part, and this part cancel out, so I have a negative 5 to the negative 1 left over, or a negative 1/5. That is going to diverge because if I take the limit as n approaches infinity of negative 1/5, I still get negative 1/5. So this diverges by nth term. Now, if I substitute in the other endpoint, so at x equals 2, if I substitute that into my f prime, I'm going to get n equals 1 to infinity, negative 1 to the n. This time I'm going to get 5 to the n minus 1 all over 5 to the n. So simplifying, that is going to be, let's see, that'll be negative 1 to the n and a 5 to the negative 1. If I use AST, limit as n approaches infinity of 1/5, I don't get 0, so then I go to the nth term, make that negative 1 to the n. I get plus or minus 1/5, so this one technically does not exist, and therefore this side also diverges by nth term. So for f prime, my interval of convergence does not include either endpoint. Okay, so then let's take a look at the integral. Okay, here's my f of x. So my integral of f of x dx is going to be the summation n equals 0 to infinity. I'm going to take the integral with respect to x, so the negative 1 to the n is going to stay there. The n and the 5 to the n are going to stay there. I'm going to have x plus 3 to the n plus 1 all over n plus 1 to undo my power rule. And then plus c, which is like on the outside of the summation, for my indefinite integral as a result. Alright, so same thing, you only need to look at the endpoints. So, at x equals, I forgot, negative 8, I'm going to look at the series. N equals 0 to infinity, negative 1 to the n, negative 5 to the n plus 1, all over n, 5 to the n, and n plus 1. So if I simplify this, I have a negative 1 to the n and a negative 5 to the n, so I'll write that as 5 to the n. I have a negative 5 left over, and on the bottom I have n, 5 to the n, and n plus 1. So the 5n and the 5n cancel out. So basically I'm looking at n equals 0 to infinity, negative 5 over n, n plus 1. So I can compare this to, let's see, we'll compare it to 1 over n squared, which converges by p-series. And then I'll do a limit comparison test. So limit as n approaches infinity, negative 5 over n, m plus 1. I guess technically I don't need to worry about the negative 5, so let's move it outside. So 1 over that times 1 over n squared, that equals 1. So it converges by limit comparison test. Now let's check at x equals 2. So now the series becomes, let's see here. So at x equals 2, it's going to be negative 1 to the n, 5 to the n plus 1, and then in the denominator, it's going to be n, 5 to the n, and n plus 1. So simplifying this, n equals 0 to infinity. I'm going to have negative 1 to the n, 5 to the n times 5, all over n, 5 to the n, n plus 1. And I'll cancel out the 5 to the n's. And this one, we get n equals 0 to infinity, negative 1 to the n, 5 over n, n plus 1. So this is going to be an AST. We'll take the limit as n approaches infinity of 5 over n, n plus 1, that equals 0. Check that it's decreasing. Numerator is constant, so yes, it is decreasing. And so this converges by AST. So in integrating, I managed to add both points, the integral of f of x dx. That interval of convergence is from -8 to 2, including both endpoints. Okay, so then I want to talk about how we can use Taylor series to evaluate things like limits. I think there are a couple of problems on your homework like this, and also obviously the integral aspect. And again, what you want to do is make sure you recognize your series both in series form and in expanded form. So let's start with this one. Limit as x approaches infinity, x plus 1. Now, sine of a function is -1 to the n, x to the 2n plus 1, all over 2n plus 1. So I'm going to apply that to this one here. Basically, sine, if you recall, are your odd powers, and they alternate in sign. So the first one was quote-unquote x. So here it's going to be 1 over x plus 1. The next one was negative, and it would be your odd power. So 1 over x plus 1 cubed over 3 factorial. And then the next one will be 1 over x plus 1 to the 5th over 5 factorial, so on and so forth. Now, if I distribute the x plus 1 through each of these terms, I get the limit as x approaches infinity of 1 minus, this will become 1 over x plus 1 squared over 3 factorial. The next one will become 1 over x plus 1 to the 5th over 5 factorial. And as x approaches infinity, this term here is going to approach 0, because you can get 1 over a huge number. This term here is going to approach 0, and all we're going to be left with is 1. So our final answer is 1 for that. Same idea here. I'm going to take the limit as x approaches 0, but I want to expand out e to the 3x. So e to the x is x to the n over n factorial. And now in place of all those x's, I'm going to use 3x. So e to the 3x would be 1 plus my quote-unquote x will be 3x. Then my next one will be 3x squared over 2 factorial, 3x cubed over 3 factorial. And from this entire series, I'm going to subtract a 1 and subtract an x, all over x. So notice if I take the entire series and subtract a 1 and subtract a x, I lose the first one, and then I'm down to 3x minus x, which is 2x plus 9x squared over 2 factorial, plus 27x cubed over 3 factorial, plus a bunch of other terms. But notice every single one of those terms there has an x in it, so I can actually divide x out of every single term. So that'll become the limit as x approaches 0 of 2 plus 9x now over 2 factorial, plus 27x squared over 3 factorial, and a bunch of other terms. But all those bunch of other terms also have x's in them. So as x approaches 0, this goes to 0, this goes to 0, and my final answer is 2. So that gives you an idea of how you use power series to help evaluate limits. Now let's take a look at the analysis, where I give you a f of x, and you have to figure out information for different things. So here I have, let's assume a Taylor series centered at 1 for some function of fx. I don't know what it is, but I want to describe the behavior then of my function at x equals 1 and at x equals 3. So at x equals 1, I want to look at different things. First of all, if I substitute 1 into the above function, everything cancels out except for the 5. So I know that f of 1 equals 5. Now I want to use my Taylor definition of each term. So I know the next term, if I had created it on my own, would have been f prime of 1 over 1 factorial, x minus 1 to the first. So matching up with this term, that has to equal -7, x minus 1. The x minus 1's cancel out, and you get f prime of 1 has to equal -7. So going along those lines, I can also find what f double prime of 1 is and f triple prime of 1. F double prime of 1, x minus 1 squared over 2 factorial, would have to equal 13 x minus 1 squared. X minus 1 squared canceled out. F double prime of 1 would have to equal 13 times 2 factorial, or 26. And lastly, f triple prime of 1 over 3 factorial, x minus 1 cubed would have to have equaled this negative 8, x minus 1 cubed. X minus 1 cubes cancel out. F triple prime of 1 would have to equal negative 8 times 6, or negative 48. So that's how you get derivative information about the center at each point by using each term. Now, f of x I know is equal to all of that. At x equals 3, I can't get exact information unless I substitute it in. I can say that f of 3, if I were to substitute it in, would have to equal 5 minus 7, 3 minus 1, plus 13, 3 minus 1 squared, so on and so forth. But unless I know what it sums up to, there's not enough information to find the exact value of f of 3. And in fact, I can even go one more step than that. I could say no interval of convergence was provided, so I can't tell if the series converges at x equals 3. But I can do part C, because the part C question says, the error in using a second order polynomial to approximate the value of f of 1.3. Alright, so let me write down my function again. F of x was equal to 5 minus 7, x minus 1, plus 13, x minus 1 squared, minus 8, x minus 1 cubed. That's the exact representation. I'm going to use a second order polynomial here. So f of x is going to approximately equal to 5 minus 7, x minus 1, plus 13, x minus 1 squared. And the question is, what would be my error in using this to approximate f of 1.3? So f of 1.3 would therefore be approximately 5 times 7, 0.3, plus 13, 0.3 squared. And therefore, if we can assume this is an alternating series, the error is bounded by my first omitted term. Now, I'm saying assuming because if you notice it goes positive, negative, positive, negative. So if I can assume that this is an alternating series, my error is bounded by the first omitted term. So my error is less than or equal to the first omitted term, the absolute value of 8, x minus 1, which is 1.3 minus 1 cubed. Alright, a couple other things to wrap this up. First of all, how to take an integral with a power series. So I have here e to the x cubed minus 1 dx. Normally you wouldn't be able to take the integral of this because there's not enough for u substitution, but we can rewrite this with our power series. So the e to the x part would be n equals 0 to infinity, x cubed to the n over n factorial minus 1 dx. Now you don't want to subtract the 1 as a separate integral because I purposely put it there for the following reason. If I rewrite this power series term by term, the first term when n equals 0 would be 1, then plus x cubed squared over 2 factorial plus x cubed to the third over 3 factorial. And from all of that series, I'm going to subtract a 1. So notice nicely, the 1 from the series and the 1 on the outside cancel out. That means I can rewrite this as a power series again, except not starting from n equals 0. I'm going to start my power series now from n equals 1. So it's n equals 1 to infinity, x cubed to the n all over n factorial that I actually want to take the integral of. Now I'm going to rewrite this so I don't have to do divided by 3x squared, which you know is incorrect. So I'm going to rewrite this as n equals 1 to infinity, x to the 3n over n factorial. Take the integral with respect to x, so that'll be n equals 1 to infinity, x to the 3n plus 1, all over n factorial, 3n plus 1, and plus c. Another integral. Find the first three non-zero terms of the fourth root of 1 minus x cubed dx. So same thing, I want to convert this into a power series. So this one, integral 1 minus x cubed to the 1/4 dx. Now, since I only want the first three non-zero terms of this, I could go through and find f of 0, which is 1, f prime of x, which is 1/4 1 minus x cubed to the negative 3/4 times negative 3x squared. So f prime of 0 would equal 0. And then f double prime, so on and so forth. But that's going to get really messy. So instead, I'm going to use our binomial expansion idea to review binomial. Binomial was if you have 1 plus x raised to the k power, this is equal to 1 plus kx plus k minus 1 over 2 factorial x squared plus k minus 1, k minus 2 over 3 factorial x cubed, and so on and so forth. So in this particular problem that I have here, my k is going to be 1/4, and my x is going to be replaced with the negative x cubed. So all I need to do is write out the first three non-zero terms. So it's going to be 1 plus k, 1/4, my x, which is negative x cubed, plus k minus 1 over 2 factorial x squared. And only the first three non-zero terms, so that's all I need. So then 1 plus negative 1/4 x cubed. This is going to be something like negative 3/32 x to the 6th. So integrating this out, I'm going to get x minus x to the 4 over 16 minus 3/32 x to the 7 over 7. And there are my first three terms for that one. And the last slide I'm going to do is to find the sum. So I have three different ones here that I want to walk through. The first one, I'm going to go through that whole integration technique with. So we have a 2n plus 1. Now what that means is ideally I want to create something to the 2n plus 1 on top so I can set up an appropriate integral for this. So I'm going to rewrite this as n equals 0 to infinity, negative 1 to the n, that's fine. The 9 I'm going to move to the top as 1/9 to the 2n, all over 2n plus 1. And I think that's it. Okay, so the 1/9 is almost ready. I just need a plus 1 for that. So now I'm going to rewrite this as n equals 0 to infinity, negative 1 to the nth, 1/9 to the 2n plus 1, all over 2n plus 1. But what I've done technically is I've added a 1/9 to the problem. So to balance it out, I'm going to multiply by a 9 as well. Now, this I'm going to rewrite as an integral. So what you have to do is think, okay, what would I integrate to get something to the 2n? Well, if you integrate x to the 2n, you get an x to the 2n plus 1 all over 2n plus 1. So that explains this 2n plus 1 and this 2n plus 1 on the bottom. Now I need bounds for it. So if I were to substitute in 1/9, I would get 1/9 to the 2n plus 1. So the 1/9 goes on top. I have no minus sign, so I'm going to put a 0 on the bottom. So we're going to rewrite this as the integral from 0 to 1/9, the summation, negative 1 to the n, x to the 2n. And notice that integral of x to the 2n takes care of the 2n, both of the 2n plus 1s, the one in the exponent and also the one in the denominator. I'm going to rewrite this since they're both technically to the powers of n. So this is going to become 9, the integral from 0 to 1/9, summation n equals 0 to infinity, and this will be negative x squared to the n But now I can use my summation formulas because that's a geometric series. So 0 to 1/9, 1 over 1 plus x squared. That makes it equal to arctangent of x from 0 to 1/9. So this becomes 9 arctangent of 1/9. Now, that's not the only way that you have to do summations. Remember, there were the 4 series that I recommended you memorize. E to the x, cosine, sine, and natural log of x. And if you can kind of morph the functions, the series, into looking like one of those, then sometimes you can figure out what these sums are as well. Like here I have a 2n factorial, which is part of the cosine x Maclaurin series. So cosine x was the series n equals 0 to infinity, negative 1 to the n, x to the 2n all over 2n factorial. So what I need to do is figure out, is there anything I can raise to the 2n and put it on top? And you can, because you can rewrite this as n equals 0 to infinity, negative 1 to the n, 1 to the 2n over 2n factorial. That doesn't change the expression at all. So now that means that cosine, this is equal to cosine of 1. All right, let's look at one last example. So here I have negative 0.3 to the n, all over n equals 1 to infinity. Now all of our series have started from 0, so I'm going to rewrite this as n equals 0 to infinity. That means I need to change my indexes here. Negative 0.3 to the n plus 1 over n plus 1. Because if I move the index down by 1, I'm going to have to bump all my expressions up by 1. Now if I separate this out, this becomes n equals 0 to infinity, negative 1 to the n plus 1, 0.3 to the n plus 1, all over n plus 1. The n plus 1s without factorials should remind you of natural log of x. So natural log of x was the series n equals 0 to infinity, negative 1 to the n, x minus 1 to the n plus 1, all over n plus 1. So notice the n plus 1s in my formula in red. Now, it's negative 1 to the n, and I have negative 1 to the n plus 1. So the first thing I'm going to do is take out a negative 1. N equals 0 to infinity, negative 1 to the n, 0.3 to the n plus 1, all over n plus 1. Notice that looks almost like ln of x, so now I just got to match up the pieces. I have my negative 1 to the n, I have my n plus 1, so that means 0.3 and x minus 1 have to match up with each other. So if x minus 1 equals 0.3, x equals 1.3. So what I'm looking at here is negative the natural log of 1.3. And I think that is it. So hopefully I didn't make any mistakes. Feel free to email me if you have any questions, and good luck studying over spring break.